Hey, Professor, if you're talking right now, you're still muted.
Thank you very much, friend. Yeah, this is, I thought I clicked on the unmute, but anyway. So, so we have quite a lot of participation, 73 tonight. I hope some will join later. So basically, today we are continuing with these components, right? This lecture 8, that's still on that topic. That's a big one, basically. So it has a sequential design that we covered somewhat last time. It has these combinational components. It has these register constructions, multi-bit register constructions, and also there is this interesting combinational shifter design, barrel shifter design. So any questions on those topics?
Could you do an example of a barrel shift? Because I watched the video, but I wasn't really able to grasp it really.
Okay, so barrel shifter would be one, okay. I'm just seeing at the discussion, is there anything new? Constraint, no, not today, okay. So before we start, maybe we can just start with this poll. Class preparedness, let's see, let's take a 1 minute to answer to this poll. Okay, so we have 66 out of 75. Let me see. Some people are joining in now, seems like. So let me wait for maybe 10-15 seconds more to get them participated. 69 of 78.
Hey, Professor.
Yeah.
I just thought of a quick question. Like you should be able to answer it like one sentence. I'm thinking.
Sure.
So we have a regular D flip flop, and then we have the asynchronous preset reset version. Is there any reason why you'd want to not have that asynchronous preset reset?
Like you mean the synchronous preset reset?
Yeah, I guess. Sorry.
So yeah. So yeah, not a particular reason, right? There are many other type of configuration of the flip flops and the resetting strategies. I just wanted to bring one in this class because the others, like detailed things, are really part of the digital design studies, which is not in our scope. So we are doing the minimum digital circuit logic study to understand the computer processor and its overall architecture. So that's our target, and that's why I didn't bring all these other configurations into our scope of study.
Cool.
Okay, I will actually hit the poll now, and we'll share the result. Seems like you almost like a 50% of you have watched the lecture videos up to this topic, and 63% has studied the lecture notes. That's good. For others, please try to do it before coming to the class. And some of you have questions. That's good. That keeps our discussion going in the class. So barrel shifter. So I have this one question of barrel shifter, and let's try to explain. Let me try to explain that. So this barrel shifter is, okay, I want to share this Jamboard. I will try to explain that through the Jamboard. And yeah. So the strategy wise, a shifting is not a very complicated operation, right? Shifting is not a very complicated operation. Let's say I have a bit pattern, like 8-bit pattern, which let's say is right, and I want to shift it this direction, left direction. Let's say 5 bit. So as an operation, what does it mean is really I pick up this bit, this bit, and shift it like 5 position, like 1, 2, 3, 4, 5. Right? So, so this bit will come in 1, 2, 3, 4, 5-bit shift. And then similarly, that means this guy will come here, and this guy will come here. What happens to these guys? These guys will be going out of the scope, right? This is not even within the 8-bit anymore. And what happens to the rest of the bits? What happens to this rest of the bits? We can imagine a 0 is incoming. So after the shift, our result become like 0, 1, 0, 0, 0, 0, 0, 2, 4, 6, 7, 8. Isn't that? Now, the other observation we can make on top of that, we want to make this shift process very systematic now. Okay, so if it is, how can we make it a streamlined, defined algorithmic steps to make this shift result? So that's our target. So we see that a 5-bit shift, this number, this quantity, amount of bit shift, 5, we can break it down into 4 plus 0 plus 1, right? Why 0? I am coming to that, but 4 and 0. So that means 5-bit left shifting actually means you shift first this whole bit pattern by 1 position, then next step keep it as it is, and then shift it by another 4 position. Likewise, if it is a 3-bit shifting, then we can do a 0, 2, 1. Means first we shift by 1, then by 2, then keep it as it is. Even we can do a 7-bit shifting, which is like 4, 2, 1. So shift by 1 position, then shift by 2 position, then shift by 4 position. Take another example, maybe 4, which is 4, 0, 0. So keep it intact, shift by 4. Now, why I'm breaking down into this part? Like, remember, this is a 8-bit number values. So shift can be anywhere, like any direction, right or left. It can be max 0 to 7, right? This value. That means if I want to express in terms of binary, I need a 3-bit to express that code, which is a positional index. If you look at it, is 2 to the power 2, 2 to the power 1, 2 to the power 0. And exactly that's what we are doing here. Like, we are trying to break down the value of the shift into steps and steps of this binary weight. So 5 is basically binary weight of 4 and 1. 3 is binary weight of 2 and 0, 2 and 1. 7 is 4, 2, 1, and 4 is 4, 0, 0. So if we define in this way, then let me just remove this thing once more. Okay, let's write down the number in 1, 0, 1, 0, 1, 0, 1, 0. So let's call it a step 0, step 1, step 2. So my 5-bit shift, this amount is really in the binary 1, 0, 1. Okay. So let's say now I want to do like a step-by-step shifting. Step 1, step 2, step 3, which is for this guy, it is 1, 0, 1. Oh, sorry, my bad. Indices are bad. These are 0, 1, 2. So 5 is basically 1, 0, 1 for us. So here 1 indicate means at the step 0 you shift by 1. Okay, shift by 1. So that means all my bit are going 1-bit shifting.
Wait, the first one means that? The one that corresponds to place to 4? That decimal?
No, this one is this one, S0. That is
Oh, we're going from, okay, got it.
0, 1, 2. And okay, so this one, I better make some boxes to mix so that we don't make a mistake here. So it comes here, this guy comes here, this guy comes here, this guy comes here, and this guy goes out of the scope. And a new 0 is introduced over here, right? So not really here, we need to make a box. Let's say we start writing the number here. And after shifting, this is 0, this is 1, this is 0, this is 1, this is 0, this is 1, this is 0. So that is the first S0 step. Now in the step 1, now we see that the step 1, it is 0 for each. That means no shifting. So it will just go in the same position at that point. So my result would be 1, 0, 1, 1, 0, 1, 0. So that's the result corresponding to this. Now we come to the step 2, which is like 1. That means I will shift by 4 position. That means 1, 2, 3, 4 here. So this guy will come over here. This guy will come over here. And this bit will come over here. And everything else will be thrown out, and new zeros will be coming in into these positions. 0, 0, 0, 0. This is 0. This one will come here. This will come here. Now that's my shift answer, isn't it? So
you're missing a 0, right, at the end?
Yeah, I think so. I think so. What happened? Let's see.
You just didn't bring it down after introducing it in the first step, whatever.
Okay, let's see. Oh, yeah. I see that. Yeah, this 0 is really this 0. Thank you very much for noticing it here. This one, right? Basically, we are talking about, okay. This one will be 0, right? And yeah, right. So we are talking about the whole thing here. Let me redo. So with that step, S2 is 1. So we are basically shifting the bits by 4 amounts. So this will be 1, 2, 3, 4. So this guy will go here. This guy will here. This guy will be here. This guy will be here. And this one will be here, right? So ultimately, we have 0, 1, 0, 1, 0. And then extra introduce 0, 0, 0. This makes sense, right? What do you think?
Looks good. Could you quickly walk us through the circuit diagram of a barrel shifter?
Yes, I'm going to do that.
Okay, got it. Wasn't sure if you're planning on it.
Okay, so now since we understand this stepwise process, right? So every shift, like 8-bit shifting, is broken down into 3 stages. Every shift is broken down into 3 stages, as 0, 1, 2. If then we make the binary of the shift amount in the consigned way, 3 bits, and place those bits onto the stages. And if that corresponding stage is 1, we shift, like for the S0 step, we shift 1 time, and 2 step we shift 2 times if it is 1, and second S2 step we shift the binary by 4 times, like left direction, right direction, but we shift. Now, as we understand that part so far, now let's look at this digital perspective.
Wait, hey professor?
Yeah.
You sent a, I wish I could like show you where I'm pointing, but you sent a 1, you put a 1 where a 0 should have gone, I think. I could tell you what index if you go back a slide or.
Yeah, that's right. I think you shifted like 4 bits instead of 5 in total.
The 0, 1, 2, the fourth from the left, that one should be a 0, right?
Fourth from the left.
Yeah,
One.
the arrow goes from a 0 as well.
The last step, you only shifted 3.
Okay, let's see. Why don't we read one more time? Okay. So till S1, this is good, right? 0, 0, 1, 0, 1, 0, 1, 0. Till this point, everyone is good, right? Now let's see what will happen at the S2. We shift by 4. So 1, 2, 3, 4. It will come here, this 0. So this will come over here. This will come over here. This will come over here, right? And everything else, like this one, will be thrown out, like it is out of the scope. These 4 are out of the scope, right? And 0 will get placed over here. Now, does it look good? Let me see, like 5 bit, right? So it is 1, 2, 3, 4, 5. So this one, then this one will come over here. This one will come over here, and everything will be 0, 0, 0, 0, 0. So 0, 1, and everything else will be 0. So that's the answer. This is good?
Looks good to me.
Okay, now move on to this concept now. So we have 3 stages, S0, S1, S2. Now at each stage, let's talk about this left shifting, left shift. At each point, we have a choice. Either we stay on the same bit, or we shift one position. So at this stage, right, at this point. So we have a choice to shift by one position, or we have a choice to stay at the same position. And that is really depending on what this value is. If it is 0, we have to choose the same bit position. But if it is 1, then we shift. So far, so good?
Professor, can you change the slide on the Jamboard?
Oh, sorry.
Thank you.
Here, so we have this choice of like either we will stay at the same bit position, or we'll shift at the next bit position, like 1-bit position shifting at the stage 0. So how can we make it as a circuit? So what we can do is, so this position has to be chosen by whether we are taking value from this guy or taking value from this guy. It really depends on the selection bit, if it is 0 or 1, right? If it is 0, I take it this bit itself, and if it is 1, I take the previous bit out of it. Similarly, at this point too, if there is a multiplexer, we can place, I have a choice of taking this bit or taking this bit as my output from this stage. Make sense so far? No, doesn't make sense?
Makes sense.
Any question? So this is the like cream of your understanding of the barrel shifter actually. Like how we are placing multiplexer in strategically different positions with the combination of the selection bits, making the whole bit is being shifted from one stage to another. Now the question becomes what would become here at the very first stage. We'll introduce an artificial 0. Either we shift a 0 in or stay the same for the first one. Similarly, for the next one, I have these choices, right? Either I have 0, which means like no shift from this stage output, or I have shift of 2. If it is 1, then I have a shift of 2. So that means it goes here, shift of 2. Oh,
Oh,
and those will go out of the scope. Other will go out of the scope. And similarly, we'll place multiplexers right at this point, coming from here and there, and multiplexer coming from here, sorry, here, and so on and so forth, right? And for this guy, initial guy, I will introduce 0 on shifting, 0 on shifting. So that will be my next stage shifting. Now stage 2, again I have choice. Of staying at the same place or shift by 4 at this stage. So that means this one will go 1, 2, 3, 4 here. This one go to the next. This one will go next. This one will go next. Everything else will be thrown off. That means we have a multiplexer right there. And this will be inserted with zeros. This becomes my final result. 8-bit shift. Question?
That makes total sense to me in a like diagrammatical way, like conceptually. But how does like in the circuit that you've drawn for the barrel shifter,
Mhm.
how do you know how do you send it 4 away? Like are the multiplexers like sending both the output number, but also something to another, like is that output number being taken in by another multiplexer? To I'm just confused, I guess. I don't know.
So I'm not sure about this question, but this
I'm not sure either.
circuit is now become your barrel shifter. It is the staged multiplexer.
Staged as in they're connected to each other, and
Yeah, exactly.
Okay.
They're electrically connected.
okay, that's it. Okay,
They're electrically all connected.
okay, that makes sense then. I think I get it.
Yeah, is an array of or matrix of multiplexer basically connected in this specific way.
Got it.
Other question?
So the 0 or 1, which tells you whether to shift or not, how does that get to all the different, are all the pieces connected in parallel as well?
Yeah, so this one is controlling the selection, right? At each stage, this is a 0. For each of the selection of this multiplexer will be connected to the S0s, right? This one will be connected to the S1, and this one will be connected to the S2. And remember, what is this? This is your shift amount, right? This is some register, some storage is storing this value 5, which is 1, 0, 1, right? So this guy will be connected here. This guy will be connected here. This guy will be connected here. 101. That's basically is giving you how much amount is being shifted, right? Now you change this value to maybe shifting 3, right? Which is basically will place 0, 1, 1, right? So that means this stage will be shifted by 1, will result in shifting by 1. This stage will be result in shifting by another 2, but this stage will not shift at all. That means effectively we are having a 3-bit shift there instead of 5. Do you get my point? No, yes?
Yes. Can you explain how this speeds things up compared to the...
Yeah, this is combinational circuit, right? So it only depends on this delay, electrical delay of this path. It's nothing is related with the clock or anything. Whereas your sequential shifter basically needs like 32 shift for the 32-bit shifting, or 8 shift for the 8-bit shift, 8 shifting, shift by 8, shift by 16 will need 16 clock cycles. So you need to wait for those clock cycles. Whereas this is like instantaneous. It's a deal. It's amount of amount of delay from when the data is present versus when this is coming. It only depends on the combinational delay of this whole circuit, which is very, very, very small. That's why it is basically is a faster shift circuit.
Makes sense. Thanks.
Hey, Professor, I think I've shored up my question. And it's easier in the slides because you have a nicely drawn out circuit diagram of a barrel shifter. Do you happen to have those so I could describe what I'm asking?
Yes, I
Or
can.
the yeah.
Hold on. Full screen. One. So you're talking about this one, right?
No, this if you go down a little bit, I think down or no up. Sorry, up. The slide 26. I think it looks like.
26.
Yeah. So I think I can just draw here. So it looks like each multiplexer has two outputs. Like it has this as an output and this, or like this one is going this way, but it still looks like two outputs. Whereas, and when you introduce the multiplexer earlier in the slides, you just showed us having one.
Hey, no. That's understanding is a little bit misnomer. Like this is
Okay.
not an output. This is not an output. This is practically I'm daisy chaining this S0, S0 and S0. The same S0 going here, connected.
So it just passes. It takes in whatever it's given here and just outputs it here.
You can say that way, or you can actually draw a specific electrical connection from that bypassing these multiple.
Got it. But like, so just as it is, as it was drawn this way, I was confused. But that you're just supposed to like imagine that.
Yeah. So
Okay.
that you asked me that, okay, this one is daisy chaining. It's basically saying that your S0 is connected to the selection of all these multiplexer. S1 is connected to all these multiplex. It is nothing with the output or anything.
And if we had to, I'm assuming there won't be any drawing questions on exams, but if you asked us to like actually
daisy
diagram
chaining
this.
is fine. Daisy chaining is fine. Yeah, that's
okay.
Fine.
Okay, cool. Awesome. Thank you. That makes a lot more sense now then. Thanks.
Okay, all right. So that's about the multiplexer, and I think we need to, in the project 3, we need to implement like 32-bit barrel shifter. So that means how many stages we are talking of. For 32 bits, we are talking of like 5 stages, right? Instead of 3. So it is like an, so we have this 32-bit shifter. That means I can define shift amount from 0 to 31, which means it is a number of bits to represent that would be like 5. That means I'll have these 5 stages: S0, S1, S2, S3, S4, 5 stages, right? 5 stages, and each stages will have 32 multiplexer, 32 marks per stage, isn't it? So 8-bit has 8 multiplexer, right? 8-bit has 8 multiplexer. So 32 will have 32 multiplexer per stage. That means total I need to deploy 5 multiplied by 32, 160 marks, 2 by 1, 2-bit, sorry, 2 by 1, 1-bit multiplexer, right? So that thing will be like, it will be connected like this matrix fashion, and we'll be doing it in project 3. Basically, this is one of the component will be constructing there. Question? Okay, let's take 5-minute break, then 8:15 we'll be back. Okay, let's get back to our discussion. So now, video. Okay, so please go to your canvas for the pop quiz 3 and see if you are ready to enter the password. I will share the password with you. So there are 53, 54 out of 81. Ready to get, we're about 81 student here in this today. $74 out of 81 are ready. I think one is said no, like you didn't find that quiz or you just mistakenly hit on that no. Okay, 78. I'll wait 5 more seconds and then distribute the password. If you're not ready, that's your problem. Quiz password. Here it go. I think few more minutes and your time will be over on that, at least for most of you. Yeah, I think quiz time is over now. Let me share my screen with you. Share. This is, I think, so far I got the quiz statistics summary as a class. Average 60% with the high 100%, low score 0%. Okay, so we could do better on this part. All right. One thing I want to discuss with you, like for some students, like every semester I see there is this little confusion about this multiplexer. When we say that multiplexer Y output follows the this input I0, I1, I2, I3. Like for some of you, it is purely a combinational logic. Like Y is a function, Boolean logic about like with this combination of input S0, S1, I0, I1, I2. So what does it really mean? These are all one bit, and Y is evaluating something. I wanted to demonstrate that with you. So what I did in the Verilog, I make some 4-bit 4 to 1 multiplexer. Means what? Means, let me see if I have the code. Yeah. So basically, I have one 1-bit multiplexer, 4 by 1. So 4 input, 1 output. With each of the input is 1 bit. That is a max 1-bit 4 by 1 multiplexer, and it has this line decoder. It has exactly similar circuit like this. Like it has a line decoder of 2 to 4, followed with the and then with a giant OR of 4 OR, and that's is 1 bit. And then I combine 4 of them to make a 4-bit 4 by 1 multiplexer. A 4-bit 4 by 1 multiplexer. And that one is basically, if you want to look at the structure, is something like this one. Where is my Zoom? Oh, there.
So we don't really need to worry about what's going on inside the multiplexer.
We don't need to, just let's look at the behavior of this 4-bit 4 by 1 multiplexer of this one. And especially I want to show you the data diagram, the timing diagram of that. But it is more likely, this is the structure. This is all of them are 1-bit 4 by 1 multiplexer, and they are basically parallelly connected. They have the common selection. S0, S1 is common between them. That's how you make like 4-bit multiplexer or 8-bit multiplexer and so on and so forth. Basically the timing diagram wise, now let me explain what I mean by the follow the path. Okay, so we have these two selection, S0, S1, right? Let me put it on the top. And I have these 4 input and output. So see, this output is following is same as the I0 as long as my selection bit is like is a 0 as a amount, right? This is 0 0, which is 0 in decimal. So as long as it's selecting the I0, it is following I0 here, 4 2 4 7 4 6, etc. And at this point, S0 become 1. So it should follow the I1 now, right? It should follow the I1, but apparently it is 40 also because at that point I1 is happens to be 40. So, but it is really following I1 if you look at that from this point. It is 40, 46, 4E, whereas I0 is basically a different value. So it is now following the I1. Now at this point, it start following the I2. Now from I1 was 4, I2 was 6. So see the change in logic, it is 1 to 6. So it is now start following output of the input 2, that bit pattern, that value. And at the output of the multiplexer, we are selecting as if we are selecting the value incoming in the I2 channel. And at this point, now it start following the, look at this, it was following I2, which is 4-1, but at this point, it start following the I3, which is 4-7. Now at this point, it is following the 4-7 that time. So this is what I mean by output follows the input. We are kind of channeling the input to the output, incoming bit pattern into the input on one channel to the output based on our selection. Make sense? Question? All right. So if there is no more question, then I think we can stop tonight. Then we will start with the module 4, I think, in the next week, which is like addition, subtraction circuit and multiplication division circuit. Please watch out for the announcement tonight and what module to start with. And work on the project too. If you have not started it, please start it. Like otherwise you won't be able to catch up on the project. All right then, good night everybody and see you on next Monday.
Oh, hey Professor?
Hey, yes, friend.
Somebody was asking about the universal gates in the Discord chat. I don't know exactly what they want to ask about, but
Universal gates are basically your NAND and NOR logic, either NAND or NOR, because with that NAND or NOR you can actually make any logic. Remember, using the De Morgan and everything, you can break it up any logic into NAND or NOR. You can make inverter gate with a NAND or NOR. So these two gates are universal gates.
How about fundamental logic gates? That's like a different thing then?
So fundamental logic gates is set of the logic gate which you can build with the transistor, which is basically inverter, NAND, NOR. So universal logic gates is NAND, NOR. Fundamental logic gates are inverter, NAND, NOR. Other question?
Professor,
Yes,
could I talk to you after class because I couldn't make it to the office hours because I have a class at the same time?
can you send me an email? Or okay, sure. I'll create a break room for you maybe. Yeah.
It won't take long. It's just like one question, not class related.
Okay. Sure. Is it about your email?
Oh yeah, that was it. I
Yeah,
was
I
wondering.
have seen it. I didn't get time to reply to you. I'll reply it by tonight.
Okay, thank you so much.
Okay, sure, Anjali.